In this last video of this entire lecture on the Harmonic measure, I'd like to give a few quick examples. So first of all, is you probably already know if M is just a usual Lebesgue measure. Let's say usual Lebesgue measure on R. Then M itself is a Harmonic measure. Okay, so it's the left Harmonic measure. It's also the right one because it's abelian. And if you just restrict to if you think about the unit circle as a subset, say 0 to 2 pi, okay, then 1 over 2 pi times m is the probability measure. That's also left Harmonic measure. Okay, so probability left Harmonic measure on the unit circle. So that's kind of our motivating example. If your G is finite, okay, so there's quite easy to see that if it's finite, then the Harmonic measure basically put the same mass on every single one of them. Okay, so your mu of each element G is, say, equals to 1 over the cardinality of your group G, then that's the probability Harmonic measure. Okay, so it's also left and right Harmonic measure. So I'll just say Harmonic measure. All right, so those are some fairly simple example. And if we think about the following, if I take R and let's just take a weight 0, and it's going to be a group under the multiplication. So this is clearly, again, locally compact, Hausdorff, and so on. So we know it has to have a Harmonic measure. So let's define mu of E to be this integral over E of this function, 1 over x absolute value dx, where dx is the usual Lebesgue measure. Then I want to show this is actually defines a left Harmonic measure. Okay, it's no longer a probability measure because your set is now compact. Well, but how do you show that? Well, there are several ways of doing that. It's essentially just a change of variable formula, or you can just say, if I want to evaluate a half-open interval, let's say AB, that's just the integral a to b. Let's assume that a and b, they're both positive. If one of it is negative, you do like two-part break into two parts. And when they're both positive, this is just integral 1 over x. So this is going to be the ln b minus ln of a, which is equals to ln of b over a. And as you can see, you can multiply ab by any constant and give you the same thing. So it's the same as mu of, you translate everything by some, say, xa and xb. Okay, that's going to be equal. And because your group is multiplicative, that's essentially just equals to the x times translate your half-open interval. And because your mu is finite on these compact, these half-open interval basically generate a Lebesgue-Stieltjes measure. And you can just simply check that this mu is going to be the left Harmonic measure. Okay, so that's essentially how you prove it. Okay, so and in general, there's something quite similar. So let's do the following result. So suppose you have some locally compact Hausdorff group under as a subset of a n-dimensional Rn. Okay, so that's locally compact Hausdorff. And suppose your multiplication is given by this kind of formula. So xy, when you multiply x and y, well, you think about them as something inside Rn. Okay, so when you multiply, you can find some ax times the y. So here ax is something inside mn of x, and then you may add some b of x that's inside Rn. Okay, so that returns some kind of product. So if your product is defined in this way, then you can do a Harmonic measure. So essentially, just what you do is you do a change of variable formula, but the formula becomes the following. So if I want to tell you what the Harmonic measure is essentially just the following. So the mu of the c is going to be the integral over e of 1 over determinant of the a of x. Okay, so the a of x, it looks like the Jacobian or the Jacobian matrix of this transformation. And you, of course, you do some absolute value, and then you multiply by the d of these x1 up to d of xn. You do the product measure of the usual the Lebesgue measure, and then you divide it up by determinant, okay? So sometimes you also just write mu is equals to determinant of these ax d of x1 up to dxn, okay? That's another way of writing it, okay? The proof is essentially just one-step change of formula using Jacobian. Of course, we need to assume the A is continuous, nice enough, and everything is differentiable, and so on. All right, so that's not going to be a big problem. All right, just as an example, if you consider the complex number, if you take away 0, okay? So the complex number, if you want to embed it into the 2 copies of R, then the multiplication, if you have x1, x2 times y1 and y2, basically you treat x1, x2 as x1 plus I times x2, and the same for y1 plus y2, I times y2. Then your multiplication becomes, well, the first one becomes x1, y1 plus x2, y2i, but so you have a negative here, so it should be a negative. And then the second coordinate, you have x1, y2 plus x2, y1. So your this one, you can write it as a matrix multiplied by the y1, y2, essentially. This is given by x1 minus x2, and then you have x1, x2 here. So this is the matrix A of x. So from there, you know the Haar measure just by this fact is essentially given by, so mu is given by 1 over determinant of this AX, which let's say dx1, dx2, and the determinant is easily computed is 1 over x1 squared plus x2 squared dx1, dx2. Okay, so that gives you the Haar measure. Okay. So let's give you one way of computing it. And I just want to probably do one last example. Suppose you have a bunch of, let's say, GI, they are locally compact Hausdorff, and let's just assume that they're actually sigma compact. Okay, so they're going to be sigma finite. All right, so you can think about their product group. Okay, that's again going to be a locally compact Hausdorff, and because each one of them you have a, let's let mu I to be the left Haar measure on this GI. Okay, then you can talk about their product measure on this the product space. Okay, so the product measure is to use this notation, product I going from 1 to n, finitely many of them. That's the product measure is going to be a left Haar measure on the product space of these GI, okay? The proof, again, is basically quite trivial, okay? The product measure on this product, when you do the integral, you can just do the left translation on each one of them. And you basically treat it as an iterative integral, and everything should be simple. And in fact, if you just take away the sigma compact, a lot of this result may still hold, okay? I'm not going to go into the technical details in full length. You can read full length book on that. All right, so that finished our example on the Haar measure.